Good afternoon, this is Schweitzer, and we're looking at a video on essentially the non-mathematical properties of gases. So we're looking at some of the external factors that affect it, the gases, and um, pretty big focus here on the kinetic molecular theory and how gases behave. So in other words, why is a gas a gas? Like how does it act like a gas? What's it like to be a gas particle? Um, so external factors, the big one here, and this is stuff that we have already discussed, is okay, external factors technically is our whole conversation of ideal gases versus non-ideal gases. Um, if uh, if there's nothing acting between the particles, then um, then we would have an ideal gas. Otherwise, non-ideal means there are some interactions. So other things that might be going on here is okay, pressure. Okay, so this is one where um, atmospheric pressure is going to start playing more and more a role in these gases as things get compressed or not compressed. So we can deal with two types of pressure. One where we have a pressure inside of a container where pressure is produced by the collision of a particle off the inside container of a wall, or pressure, atmospheric pressure, where you're literally standing under a pile of air, and it's physically with gravity forcing down on top of you. This would be the same thing as if you were going swimming in a pool and you jumped in and swam down towards the bottom. And of course, at that point, you feel the pressure, all the weight of the water pushing on you, and all the air on top of that. So, pressure. What are the main units of pressure and what are the conversion factors? So, 1 atmosphere is probably our main one we use. The next most common one would be torr, uh, or it's a millimeter of Hg, and 760 of these is equal to 1 atm. Atmospheric pressure, if you're standing on the ground, what factors will affect the level of pressure that you feel? Okay, so essentially you feel all the weight that's above you. The atmosphere of Earth is pretty constant as far as its depth is concerned. It's not like there's areas of the Earth that have a thicker atmosphere. That's, so really it's the constant, it's the makeup of these particles. Sometimes you get a lot of water in the air, and that happens actually to be lighter, 18 grams per mole, as opposed to if it was dry air and the individual particles, again, the same consistency or density, would be 28 grams per mole. So high pressure systems typically tend to be drier. Um, Other things might be that as you go higher up in the air, then you're literally standing higher up, so you're not having nearly as much of the atmosphere above you, so the atmospheric pressure is less. Um, as far as chemistry is concerned, what are some of the major effects caused by atmospheric pressure? Um, I guess weather really is what it comes down to. Weather causes is high and low pressures and that sort of stuff. Not something that really would concern us too much in chemistry, at least not in this class. All right, pressure inside a container. A sample of gas is often presented by a particular diagram as seen to the right. Draw a sample of gas. What things do you have to keep in mind? What causes pressure inside a container? What factors would cause the pressure to change? So this is a really common question. We're trying to compare or describe why pressure changes inside of a container. So the number of collisions that a particle makes off the inside container of the wall, and then so number of collisions. Okay, and then if the particle is traveling faster, so that's one option. So as you were to raise up the temperature, then it would travel even faster and hit the wall with more frequency. and then also the force that the particle hits with. As you raise your temperature up, you also end up having a greater amount of force. So not only they hit more often, but they hit with a larger force. Those are two things that we would like to look at. So what causes pressure inside a container? It's really important to realize that pressure inside a container is caused by the collisions of particles, okay, with the inside container of the wall. Container wall. And that's really important, and we'll see that as well. And they're going to want you to reference temperature and how these factors work. What causes the pressure to change? Like I mentioned, more collisions. A heavier particle might be going slower for a given temperature, but it hits harder. So really temperature is the main way to change the pressure. You could also take the gases and push them into a smaller container. And now they might be traveling the same speed, but they hit off the wall more often because the walls are literally closer. And as they hit more often because they have less room, that also signifies an increased pressure. Molecular velocity versus average kinetic energy. So this is a review. Average kinetic energy is, of course, the temperature. This is something we've hit on a lot. Kinetic energy is equal to 1/2 the mass velocity squared. This is the average here. And this is the temperature here. This is the molecular velocity. Molecular velocity. And we want to make sure we understand that concept. As this goes bigger for a given temperature, as this gets bigger, the particles travel slower. Student hypothesis: the particles in helium balloon are not traveling the same speed as particles in the oxygen balloon. But all particles in helium balloon are traveling the same speed, just so we nullify. Okay, so first of all, there's some true information here, there's false. Helium balloon, the particles in helium balloon are not traveling the same speed as the O2. Correct. These ones are traveling faster. These ones are traveling on average slower. On average. Okay. So when I say average, okay, it's poorly spelled word average. On average, these guys are traveling faster because they have a lower mass, so higher average molecular velocity, but nullified because helium balloons are all traveling the same speed? No, it's an average speed. Okay, so which balloon has the greatest average kinetic energy? They're the same because they're the same temperature. Which one has the greatest molecular velocity? The one with the lowest mass, which would be helium. The oxygen weighs 32 grams per mole. This guy weighs 4 grams per mole. This is not a linear relationship, so you can't say it's traveling, whatever that is, like 32 divided by 4. 32 divided by 4, 8 times. You can't say that the helium's traveling 8 times faster. It's not a linear relationship. All right, you've seen this already, so it's time to look at this again here. It's Maxwell's distribution showing kind of what's going on here. Again, we have oxygen at 25, oxygen at 1,000 degrees. A couple of things you want to keep in mind about this. One, always start here. And area under the curve should be the same. So that peak has to come down to maintain area under the curve. Area under the curve represents total number of particles. Again, it's something that we've already talked about a lot, so I shouldn't say a lot, but it's been mentioned in previous videos, so we'll just we're going to move all along this stuff pretty quickly. Same substances at different temperatures. Helium 25, helium 100. So again, we did this already. Start here, go like that, and then start here and go like that. This is the 25. This would be like the 100. Just saw one previous. Here we have helium 25, oxygen 50. Again, I could even make that 25. It doesn't really matter. Helium will be traveling faster, so it might look like this. All right, and the oxygen, same number of particles. So I want the same area of the curve, but they're traveling. I'm going to erase that here. The oxygen is traveling slower, so increasing molecular speed this way. So let's do the oxygen first, and then we'll do the helium second, like that. Oxygen, helium. Looks like I have too big of a air in the curve here, but I think you get the point. They're basically the same graphs. This would be the helium, and this would be the O2. Again, important stuff there. The gas particles in vessel 3, this guy, are represented by the diagram above. The lengths of the arrows are represented by the past. Take a moment, think about this one. All right, what do we got here? So in this situation, gas particles, vessel 3, 27, are represented by above the lengths of the arrows, the speeds, the particles, which the best diet represents the particles when heated to 127. So we're going from 27 to 127. So we don't want to gain any particles. So that one's out. And 1, 2, 3, 4. We didn't break anything apart, so that one's out. We just need to have the same particles traveling on average faster. So on average, longer lines. That would be this guy. This one looks like it got colder. All right. Next, there we go. All right, effusion versus diffusion. What's diffusion? That's just, they're literally particles due to random movement, particles from high concentrations moving to areas of low concentrations. We see this all the time. Smells just go from areas of high concentrations and eventually they spread out and they just become lower concentrations. That's what happens. It's due to the random movement of particles. We call that diffusion. Effusion is the same thing due to random movement, just slowly bouncing off walls and things. It slides through a hole. That's the only difference. They make their way through holes. So eventually they'll get to the point where they're the same concentration on both sides. Diffusion is really, we're talking about effusion, cell movement across cells. What factors affect the fusion and diffusion? Well, probably concentration is one of them, but the other one more likely would be just temperature, because the higher the temperature, the faster this random movement is, and the more often they have a time to hit a hole. So, for example, a helium balloon when I was a kid would really only last about a day, and this is because there are little microscopic holes in the balloon, and as the particles are flying around, they would accidentally or inadvertently hit a hole and skip out. Helium would be like one day. Overnight, your balloon would be deflated, but regular oxygen or regular nitrogen, this balloon might last 3, 4, 5 days. Because of the much larger mass the particle has, the slower the velocity, and therefore it's just a slower lumbering particle. And because it's moving slower, it just has less of opportunities to hit holes and get out. So even though these two particles, this one versus this one, are the same temperature, they might be the same average kinetic energy, this particle is traveling much faster and therefore effuses or diffuses faster. So temperature is a factor, concentration is a factor, also molar mass, more molecular weight is a factor. All right, this is the calculation of it. Not a super common calculation. We combine these two to form essentially one number, which is the rate, like how much rate faster than one versus the other. How much faster is 1 versus 2? That's one number. So if its number is above 1, then the first guy, this would be the rate of M1, and this is the rate of M2. That's why the 2 is there. So that means that 1 is effusing faster, which typically would mean that it has a lower molar mass. If it's below 1, then then it's a slower moving particle. It's not effusing as fast. But either way, you can then put your molar masses in here. And so we typically solve for this as one whole piece. So we typically have three variables: the mass of 2, mass of 1, and then it's the rate. If you reverse these things, if you have for example, you can do 2 gas particles, and if it's slower, all right, then that means that, or if it's above 1, that means 1 is faster effusing than 2. If I reverse this, we'll get a number less than 1, which just means that 2 would now be on top, and it just means that 2 is slower than 1. So simple plug and chug math problem. And there's an example. Take a moment, take a look. All right, 0.5 mole sample of helium, 0.5 mole sample of neon. So this guy is really small. This guy's a little bigger. It's got a volume. Each container has a pinhole. So we're talking about effusion. Which gas, helium and neon, will escape faster and why? Take a moment. So you can get rid of, get rid of neon. Get rid of that guy, it's helium. It's got to be it. Take a look at the reason. Very important. Okay. Again, these are some external factors, and we've been dealing with some properties as well of effusion. All right, kinetic molecular theory. I've already been talking about this. Temperature is just the movement of particles. And you should realize there's two types of movement. There's translational movement, and there's rotational movement. Obviously, if something goes from a solid to a liquid to a gas, all we're doing is gaining more rotational and then some translational movement. Increasing temperature is going to cause an increase in movement. Pressure, this is really mathematically is force divided by area. That is what pressure is. And typically speaking, inside of a container, pressure is created when an object applies pressure to a wall due to a collision. So the force really is collisions per area. Of course, we're assuming a given particle with a certain mass. Heavier particles heat up would hit harder, or if they're traveling faster due to increased temperature, they hit harder. But in general, collisions per area is going to be proportional to the force per area or pressure. So the more collisions you have, the more pressure you have. And that's important to understand. The two factors then would be affecting the collisions would be, well, how fast a particle is traveling, and then the number of collisions. So we'll see that in a moment here coming up. All right, so typically we describe the kinetic molecular theory and how gases work with 3 containers. These are the 3 variables that we'll look to see how they affect each other. Obviously, particles is also something that is important. So a rigid container, we're going to start holding some things constant here. So the volume is constant in a rigid container. You should be aware that if I were to increase my temperature in a rigid container, the particles would start traveling faster, and therefore they'd have more frequent collisions. And also more forceful collisions. And that should be obvious. forceful collisions and more frequent collisions. They're traveling faster, so on average my vector lines are longer and I get more pressure. A balloon, technically in a balloon, the pressure on the inside equals the pressure on the outside. If the balloon's not changing its size, then the two pressures are considered equal inside out. So pressure is not changing. We're not going to change the number of particles now, although if you increase them, blow more air in, it gets bigger. Same thing with this guy. I mean, if you blow more air in, the pressure goes up because you have more collisions. So here, once again, if you increase your temperature, then you're going to have a temporary change of pressure. And this is going to cause particles temporarily to move fast. Well, they're going to move faster regardless, but you would have more collisions on the inside, which creates a temporary increase in pressure, which causes a volume to increase. So it's collisions per area. So what happens is the collisions temporarily go up, which causes the balloon to expand. Then the collisions start coming down. So really your area got larger. The reason why your collisions go down is because you get more area. So pressure is force per area. And we're eventually here going to increase this, but then we increase this. So we're back to our original pressure. So the pressure didn't change, but the volume did go up. So as temperature goes up, the volume goes up. Here, we're going to hold the temperature constant just for an example here. So this is being held constant, being held constant. And you should be aware that as I push down a force on this thing, that my particles are just in a smaller area and they collide more often. So more collisions, more pressure. So reduced volume causes increased pressure. Thank you very much.